Ever wondered how doctors transform blurry medical scans into crisp, detailed images of the human body? It's not magic, it's AI, specifically a groundbreaking technique called PHMDiff. Let's dive into how this innovation is rewriting the rules of medical imaging and why it could revolutionize healthcare. Here's the challenge: medical scans aren't always perfect. Motion artifacts, low-resolution hardware, or equipment limitations can leave images unclear. Traditional methods like GANs, generative adversarial networks, often produce results that look plausible but lack precision. Think of a smartphone camera guessing the details of a photo, resulting in blur or unnatural textures. Even diffusion models, which have dominated image generation, struggle with fine-grained details. PHMDiff, however, is different. It's like hiring a master artist who not only understands composition, but also knows exactly how to reconstruct every brushstroke. So how does PHMDiff work? Imagine building an image in stages, much like a painter refining a masterpiece. It starts with a low-resolution skeleton of the scan, then incrementally adds layers of detail, first broad shapes, then textures, and finally minute features. But here's the key. During training, it uses random masks to obscure parts of the image, forcing the model to infer missing information based on context. This is akin to covering sections of a puzzle and training the AI to deduce the hidden pieces by understanding the relationships between visible ones. What makes PHMDiff revolutionary? Two core innovations. First, it employs a pyramid hierarchy, a multi-level framework where the model processes images at varying scales. Starting with coarse structures, like organ outlines, it gradually refines to high-resolution details, such as microvascular patterns. Second, it leverages multi-scale masking, dynamically adjusting how much of the image is hidden at each hierarchical level. This balance ensures the model retains global context, e.g. organ shapes, while mastering local precision, e.g. tumor margins. Plus, it integrates a transformer architecture, which excels at capturing long-range dependencies in images. Think of it as the AI's ability to understand how distant parts of a scan relate to each other. The data speaks for itself. PHMDiff outperforms state-of-the-art methods in PSNR, peak signal-to-noise ratio, measuring clarity, and SSIM, structural similarity index, quantifying how close the output is to the original. In clinical tests, it achieved 23% higher PSNR in MRI to CT conversions and corrected corrupted scans with 94% accuracy. Its efficient training process, reducing computation time by 40% compared to diffusion models, makes it viable for real-time applications, from emergency diagnostics to radiology workflows. Why does this matter? Sharper, more reliable images enable earlier disease detection, reduce diagnostic errors, and minimize the need for repeat scans. For hospitals, it's a win-win: lower costs and faster patient throughput. And because PHMDiff is open source, researchers can build upon its foundation, accelerating breakthroughs in AI-driven medicine. So the next time you hear about AI in healthcare, remember, technologies like PHMDiff aren't just about algorithms. They're about transforming ambiguous data into life-saving clarity, pixel by pixel. Stay curious, and let's keep exploring how AI is reshaping the future of medicine, one scan at a time.